This is Ed. I'm not sure what we're seeing on screen right now, but welcome to another episode of Mathematical Games. I don't see anything in the YouTube channel. I see an error occurred, but I'm going to go ahead. Um, this is episode 30 of Mathematical Games. And this episode, we're going to talk about measuring the universe. In the mathematical games columns in Scientific American, Martin Gardner covered many different topics over the course of 25 years and put out 15 books that were collected editions of his columns. In almost all of those books, he had to update material that was in his columns because there were new discoveries. And as a result, there was this constant emphasis on updating the records for things that had been discovered. So part of this series, I've been trying to update more of the items that have been in Martin Gardner's columns. So for this episode, I'm looking at his column on extraterrestrial communication, where he made the point of talking about Percival Lowell in 1895 and what that inspired. Percival Lowell wrote a influential book on Mars called Mars, and that got H.G. Wells and Edgar Rice Burroughs to write their books about fiction on Mars. When Pluto was found, it was decided by the discoverer, Tom Bow, if I remember right, that the planet would be named after Percival Lowell in some way, so they chose the name Pluto. And later in the column, he mentions in 1960, Project Ozma tried to find communications from Mars and other places in the universe with listening at the hydrogen line, 21 centimeters. And here's the column itself. As oddly, Claude Tombaugh, the person who discovered Pluto, wrote back to this column, and they published it. And Martin Gardner responded to Clyde. I can't remember what the person's name is, but they had a back and forth on the legacy of Percival Lowell. So those canals on Mars are now called the Valles Marineris, named after the Mariner mission. One other item that Martin Gardner talked about in his column was Nikola Tesla was one of the first to claim to have communications with Mars, that he heard strange signals when he powered up his vast amount of electrical equipment in Colorado Springs. So you can read what Tesla said here. We're not actually sure what he heard, but it's one of the first cases of radio astronomy. In 1930, Karl Jansky verified that there were many different strange signals happening that he was able to listen to, and that started the whole field of radio astronomy. One odd thing, Nikola Tesla did a lot of this work in Colorado Springs. I happen to live 1 block away from where his lab was set up. The Colorado School for the Blind was right next to where his lab was. And I used to drive by that area every day. So in addition to communication, we also want to measure things. So here's the time, November 16th, 2018. This is the moment in time where the new SI units became official. And Michael Trott wrote a great blog about it. You can read it here. So at this point in time, they came up with a method for measuring everything based on universal constants. These are the items that are being measured: second, meter, kilogram, ampere, Kelvin, mole, and candela, but they're all based on physical constants. So, for example, the candela, they measure the luminosity at a particular frequency, 540 terahertz or 555 nanometers. Now, I would have gone for 547 terahertz or 547 nanometers, which is chartreuse. Or I may have chosen the green laser. However, the color was decided in 1924 before either of those existed. Mercury green would also have been a good choice. But apparently, 540, 555 is the color that's best detected by the human eye. In fact, when they're doing tests on detection, it's possible for the human eye to detect just one photon in a very, very, very dark area. And this place where these are equal, 547.5, that's based on the speed of light divided by 1,000, the square root. And this is basically what that color would look like. The constants are exact by definition, and here's a nice chart. Of course, for candela, they didn't use green. They should have swapped these two colors. The first set of standards, though, came in 1799. And there was a fight about this. There was two different arguments for what should be picked. Quite a few people wanted the meter to be based on the 2-second pendulum, which would be a length of 99.4 centimeters. So that was one proposal, but the argument against was that the gravity on Earth varied slightly. So it wasn't, they couldn't be repeated everywhere, but I kind of see that as a false argument. Once you know what the change in gravity is, you'd be able to use that when you came up with a meter-long bar, which you could micro-adjust with a weight on it, and that would make very small adjustments to the length you picked. Various people wanted the pendulum clock length to be used. For example, Christian Huygens, Jean Picard, and also Thomas Jefferson was one who wanted the meter to be based on the pendulum. He wanted to redefine the yard based on that. But others wanted a meridian approach with 10,000 kilometers from equator to pole. And some of the people going for that were Lagrange, Laplace, the father of modern chemistry, and some philosophers. And in the end, the meridian won. And as such, the distance from the equator to the pole is 10,002 kilometers because they made various mistakes. They got 4 digits of accuracy. If they'd gone with the pendulum instead, the measurement would be 10,032 kilometers from equator to pole. So it would have been a change of 60 kilometers in this meridian measure. Despite difference of gravity, if they'd gone with the pendulum version instead, they could have gotten 70 digits of accuracy anywhere in the world. And this meridian argument was basically thrown out because it was so hard to replicate that they eventually just cut a bar anyways, which is what they were trying to avoid. So they should have gone with the second pendulum in 1799. So they used defined constants to measure everything else. Speed of light, the hyperfine frequency of cesium, the Planck constant, elementary charge of an electron, we'll be covering all of these as we go through the talk. And from these, we get various derived constants. And I talked about many of these in episode 28. For example, how to define a kilogram using a Kibble balance and these defined constants. And you can go through the various derivations, and these derivations are in many different places. And with these constants, we have these nice posters showing how everything links together. So back to the Gardner column, one of the people prominently mentioned in that was Frank Drake, and he came up with the Drake equation based on various variables. You could calculate how many different civilizations there are in the Milky Way galaxy or in other galaxies. And it turns out with even the most conservative estimates, this one is probably too conservative because it basically says there's no civilizations in the galaxies, and we know there's at least one. So this is a way of estimating how many different communications there, civilizations there might be. Let's see here. Later, after after that column, they tried the Arecibo message, and it was Frank Drake and other people and Carl Sagan who came up with this particular tessellation to try to explain various things to people that might be listening. At the start is the numbers 1 to 9. There's a base digit that's always set, and then the rest is a method in binary. And then based on that, these are the important molecules: hydrogen, carbon, nitrogen, oxygen, and phosphorus in stacked form. And these are the ribonucleic acids, and various other constants are all worked into this message. I'm not sure how well a person could decipher this, but this is the message that was sent. So later they wanted to show other items. So this was picked. It was one thing Varngard mentioned in his comment, the 21 centimeter hydrogen line. So the spin flip transition line, this item here is 21.1 centimeters. So with this, we can derive what Planck's constant is. And here's some data for that. The energy of a photon is equal to its frequency multiplied by the Planck constant. So here's where the 21 centimeter hydrogen line is. It has an energy of that 6 micro electron volts. The cosmic background is slightly more powerful than that, and visible light is 400 million times as strong as this hydrogen line. So here's where we start seeing at the red, the amount a photon needs to affect an atom to knock a hydrogen atom is this much, slightly more than red. A X-ray photon is 50,000 times as powerful as red light, and our eyes can safely handle light in this range. Sun is about 100,000 lux. So this item up here in the Pioneer plaque That's what this is, and the plaque was made so that this length is 21.1 centimeters on this plaque to get an idea of how large this plaque is. The hydrogen line is the fourth restricted zone in the broadcast spectrum. And it turns out that all these restricted areas in the broadcast spectrum deal with various chemical elements that would put out a signal at that item, like carbon monosulfide is in this range. UHF, if you remember what UHF channels were, is one of the ones that turned to restricted, and that's where redshifted deuterium would be. There's usually two frequencies that are looked at now in radio astronomy. There's the actual value and a redshifted value. So we've got many different ways of measuring things. Here's a few of the measurements in history. We've got feet, paces, cubics, carats, irons, twips, Gutenbergs, Irish miles, skeins. All the numbers here are integers. For example, there are 2 shaftsments per foot. So this is another item I did on community. This item at the top, I always kind of wondered what that was, so I finally looked up what it is. It's the cosmological quantum point length, and here's what it is. It's a fraction of a meter, 88 micrometers, which is just slightly larger than the largest cells. The largest cells are about 50 micrometers. So this looks wrong. I'm just going to take that out. It is the inverse fourth square root of the cosmological constant. And that represents a characteristic length apparent associated with the accelerated expansion of the universe. So this is Einstein's, what they finally calculated to be. It's the fourth, 1/4 power is this much micro electron volts, which corresponds to 88 micrometers. So the cosmological constant problem, we can predict what that constant is, and we can also measure what that value is, and they are off by a factor of 10 to the 120. So there's a question about vacuum energy and expansion in there that still hasn't been resolved. A related item is the Casimir force, which is the vacuum energy between parallel uncharged plates. And they're finally getting pretty good at measuring this. And this is the calculation. On archive, the cosmological constant is the most popular constant to talk about, even greater than the speed of light. So the first big measurement was measuring the size of the Earth. And Eratosthenes came up with the method of that by having a friend put a pole in Alexandria while he was in Syene. And with that, he figured out the angle was 7 degrees off, and he was able to calculate the radius of the Earth with that. Much later came Kepler. He was trying to figure out how to fit the universe into Archimedean solids, and he came up with very accurate measurements. And as a kind of annoyance, he figured out these laws. But he was much more keen on the fitting things to the Archimedean solids. So this was kind of a afterthought in his journals. However, it turns out to be very important. And one of the items is this last item: the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis. And here's some examples of this. We can plot out different ellipses that have the same semi-major axis, and they all end up working the same in time. Even though the orbits look slightly different, the complete orbit is the same each time. And everything, if you map the items in the solar system, you get a nice straight line. So this was one of the things that people started looking for, was how do you get, based on the data that's out there, how do you get something that comes up with a straight line to show that there's a proportion? Newton used Kepler's third law to come up with the law of universal gravitation. He basically looked at the Kepler's third law, looked at circular orbits, and from that he deduced that force is gravity times the two masses divided by the radius squared. So with that, you can calculate the force that keeps the moon in orbit. The next item that was measured was the astronomical unit by Cassini and Richter. They figured out the parallax of Mars by going to opposite sides of the planet, and based on where the parallax angle of Mars was, they were able to calculate the distance between the Earth and Mars. And they knew the relative distances of the planets thanks to Kepler's laws. They knew that Jupiter was 5.2 times farther than the sun than the Earth, but they didn't know what the actual distances were. And Cassini's measurement of the Earth-Mars distance let them calculate the length of the astronomical unit, the distance between the Earth and the sun. Once that was known, they knew, since they knew the relative distances, they knew where everything else was. Cassini also developed the Cassini oval, which is shown here. The next item was Romer. Old Romer determined the speed of light by looking at the moons of Jupiter. He noticed that when the Earth was on different sides of the sun, that the length of the time for the eclipses for the moons was different. And based on that difference of times in the eclipse, he calculated the distance of Earth's, the diameter of Earth's orbit. And that with that, he calculated that the speed of light was 214 kilometers per second, which isn't too far off from the actual value, about 300,000 kilometers per second. So with that, they first came up with a definition for the speed of light. Around the same time, Bessel measured the parallax of 61 Cygni. With that difference of the basically measuring on both sides of Earth's orbit, and with that, he was able to measure the distance to a star. Similar to these, Lavoisier noticed there's a lot of speculation on how chemistry behaved. He basically sealed items away when they reacted, and he was able to weigh everything that happened before and after an experiment. And he basically showed that there was no loss of mass, which was a theory at the time. Matter could change its state, but the total mass remained constant. So that was an important thing to figure out. And Proust noticed that the ratios of all these different reactions would always be in the same proportions. So those two things, that mass remained constant in a reaction and that the proportions remained constant in a reaction, were two important facts to nail down in the late 1700s. A next experiment was to figure out Earth's density. They first did it by measuring the mass of this mountain. They did a pendulum next to this very nicely shaped mountain, and after many different measurements, they were able to get a calculation for the density of the planet. And then just a few years after that, Henry Cavendish came up with a torsion balance technique, which was more accurate, and Cavendish result was slightly better than the result of measuring this mountain. Roughly the same amounts, though. The Cavendish experiment is still one of the best methods known for measuring gravity. They use much better equipment now, but it's still basically the same technique. The Doppler shift was first done with binary stars, which is something I didn't know. Doppler noticed that the colors of two different binary stars, one moving away, one moving towards us, would have slightly different colors, and the color shifts would swap as the stars changed places, and so that the other one was going away and the other one was coming towards us. 3 years later, Buys Ballots, who's probably the worst possible name for a politician, he discovered that the same effect occurred for sound and was able to prove it. So here's one of the demonstrations we have on the Doppler effect here. The first measurement of the speed of light on Earth was by this French physicist. He came up with a method of gears that would measure the distance between two high points, 8 kilometers apart. And with this cogwheel method, he was able to come up with the speed of light. Around the same time, Boltzmann noticed that the behavior of atoms and molecules followed certain laws, and the measure of entropy came out to be a constant. So the observation that he made, which was first really celebrated by Planck later, Max Planck later, Planck called this the Boltzmann constant, and that's where it stuck. Boltzmann was the first one who noticed this property. When they were trying to figure out how radiation worked, Stefan and Boltzmann came up with a law to explain the behavior. Unfortunately, it didn't work for visible light. This black line here was what their theory would explain, but it didn't work for various wavelengths, and this was known as the ultraviolet catastrophe, which was solved by Max Planck by introducing quantum effects. The spectral radiance of a black body at a frequency v and a temperature T is resolved with this use of Planck's constant and Boltzmann constant. So with the plot, this item, which would continue to go up, has a nice predictable plot which matches what's measured for various light frequencies. So Planck was able to come up with equations which match this chart perfectly, and that's considered to solve the problem of the ultraviolet catastrophe. So With this, quantum physics got started, and all his various measurements, he came up with equations which matched the measurements. A item that followed shortly thereafter, well, Einstein and others were writing many papers about quantum material. Rutherford figured out how half-lives work and came up with the concept of radiometric dating, so that if they could look at a rock and they could figure out what its material was at the current moment and what it probably was in the past, they could figure out how old an object was. That was a way of measuring into the past. Later, William Libby developed the idea of carbon dating in the late 1940s. And at the same time as this radiometric dating was found out, Einstein came up with E equals mc squared. A few years later, the first really big measuring of the universe came out from Henrietta Swan-Leavitt. She was plotting the periods and luminosities of Cepheid variable stars. I mentioned earlier how Kepler came up with a straight line when he mapped out the periods of the planets versus their eccentricity, one of the items of a hyperbolic of a conic section. She found the periods and the luminosities on a log plot made these straight lines, and with that, she was able to predict that if you knew the frequency of a Cepheid variable star, you would know its actual luminosity. So the apparent luminosity would let you measure the distance to that star, whether it was in our galaxy or in another galaxy. And that's exactly what Hubble did to figure out the distance to the Andromeda galaxy. So there's various different Cepheid variable stars, type 1 and type 2. The type 1 is what Leavitt was measuring. There's also the type 2 Cepheids, which have a slightly different formula. There's also the Lyrae variables, which have a nearly constant absolute magnitude. So they don't vary. You just need to know that it's this type of star, and you know what its magnitude will be. And there's also the Mira variable stars. So that's 4 different types of stars that can provide standard candles for measuring distances. And here's an example of a calculation. Here's a whole bunch of different Cepheid variable stars, and they make a linear growth pattern based on their expected distance and their periods, their observed magnitude. In 1960, the fine structure constant was noticed. If you know the hydrogen spectrum, it basically looks like this. But if you zoom in on one of these colors, it's actually several lines. And he noticed that if you measured the different ratios between what's coming up with the red line, for example, you get this constant value, the fine structures constant, which they believed was 137 for a while, but then they were able to come up with more accurate measurements later. And there's various ways we can come up with this constant based on other constants that we know. And here's a whole bunch that Michael Trott came up with, and all different ways of defining the fine structure constants based on other constants. Here's a little bit of what the fine structure constant looks like. If we change the quantum period, the ratios over here matches the fine structure constant. And as we add in more lines and do shifts, we get different changes of how these lines line up. The Boltzmann constant came up again in 1928 when noise was being measured. First in 1905, Einstein looked at Brownian motion, and he predicted that this measurement for noise would be something that you could calculate, but there wasn't a way of testing it. Well, it turned out that was wrong. In 1927, Johnson figured out a way of testing it, and he worked with Harry Nyquist, who was an expert on thermodynamics, and they published a result on how you could do this measurement that Einstein predicted, what's now called Johnson-Nyquist noise. So the magnitude of the noise is 4 times Boltzmann constant times the temperature times the resistance of the electronic device you're working with. And here's a calculation for it. So this item, the Hubble Webb Telescope, if you take your digital camera and basically completely seal off the lens and take a picture, you won't get a purely black photograph. Instead, you'll get a gray photograph with a little bit of noise in it. The amount of gray that is sort of based on the temperature of your phone. So if you're holding it, it'll be more gray than if you've kept the phone in the freezer. So this was one of the reasons they cooled down the telescope, so that you could avoid this Johnson-Nyquist noise. You also want to avoid radiation of any form, because you're basically trying to figure out the radiation sent to us by stars that are billions of light years away. So the more you can cool down the telescope, it's near absolute zero out at a Lagrange point. The cooler you can get it, the better your photographs will be. The resonance clock was developed in 1955 using cesium atoms, and that was the most accurate way of measuring time for a while. There's new methods now, but they're not ready to redefine what the second is yet. Another experiment at about the same point was they wanted to figure out how biology worked, and they noticed that if they grew bacteria in a slightly radioactive medium and then changed it to a different radioactive medium, that the density of the DNA over time would basically show a split of exactly half. Each DNA molecule, when it's split, it would be half with the original 15 nitrogen base in its atoms, and the other half would have 14 nitrogen. So basically, they proved that the DNA molecule split. The DNA molecule basically came out from this photograph. This was a photograph developed by Gosling and Franklin, who showed it to Maurice Wilkins, who showed it to Watson, and he showed it to Crick. And Watson and Crick were able to deduce, based on Crick's knowledge of the diffraction pattern of a helix, that the DNA molecule would have a helical structure. And slightly later, the cosmic radio background was discovered by Penzias and Wilson. So it has a constant temperature of that, and they've managed to come up with very good maps on the cosmic microwave background. And this brings us sort of back to where Gardner wrote his column in 1966. So there's various different lengths that you can figure out that have different scales. The radius of a hydrogen atom is a good one. The diameter of a DNA helix is about 2 nanometers. So these are different lengths that have a fixed length. Some of them are spectral lines. We also get biology items. For a replicatable distance or length anywhere in the universe, one that you could do is come up with a critical radius for plutonium or uranium. This is where it starts blowing up or melting. 21.1 is the hydrogen line. And then we've got the diameter of a neutron star and a white dwarf. The potato limit, where a asteroid starts becoming spherical, is about 200 kilometers. Another distance is wavelengths of light. So there's various dangerous photons that don't come to us because they get filtered out by our atmosphere, which is somewhat convenient. So below 200, they are blocked by these absorbers. In our range of 400 to 700, there's not many absorbers in that area. But then above that, hydrogen or water and oxygen start absorbing things again. And then there's a whole bunch of blockage above that point. So many of the more dangerous photons just get filtered out by our atmosphere. And that's one reason astronomers use high altitude balloons and satellites to observe ultraviolet and infrared, because Earth blocks those bands of light. So here's various spectral lines based on color that correspond to exact items in important spectras. And here's the hydrogen spectrum again. So if we communicate with other aliens and other worlds, there's various things we can expect. We could probably expect them to recognize numbers, geometry, and time. They'll hopefully have various physical constants they've noticed, like the speed of light. They probably know about chemical elements and the electromagnetic spectrum. They probably have measurements, but we don't know if they are in our pre-2019 area, where we have all sorts of different crazy measurements, or whether they've come up with something more based on physical constants. They'll probably have languages, and they'll probably have itemized lists. So for calculating distances, we've already mentioned the Cepheid variable stars is one way of measuring distances for the universe, but there's more. So it's called the cosmic distance ladder. So one item that can be done is type 1A supernovas. They always follow this particular pattern here, and there's a peak luminosity of minus 19.1, about 5 billion times brighter than the sun. And there's very little variation for this particular type of supernova. So whenever there is a supernova, pretty much anywhere in the universe, we can figure out what the distance to it is based on its luminosity. And they also look at this particular plot of its frequency, of its intensity, because it always follows this particular thing. There's the nickel crash and the cobalt crash. They can basically plot this to what they observe to get exact measurements. So even if there's dust or other material that's blocking what's happening, they can get very accurate pictures. This item up here, this is what's called the tip of the Hertzsprung-Russell here. When a star goes through this and hits this peak here, this is another thing that gets measured before it goes back down. There's also things like the velocity, dispersal, and relations for spiral galaxies. So these are other items that can be used for measuring distances across the universe. One new item is the chirp mass distribution, which still isn't well understood. We've got all these various chirps of colliding black holes and neutron stars, and then there's this gap, and then we get a lot more collisions. But there's never seems to be anything in this range, and this is now known as the chirp mass gap, because out of thousands of different observations, it's weird that there's this one range that gets missed. One other strange item is the distances between galaxies. And there's a constant. It's not the closest galaxy. It's that usually for any galaxy, there's another galaxy that there's a particular distance away, or was a particular distance away in the past. And that's explained by uh, events after the Big Bang. There was a early hot, dense universe, and anytime there was a sound wave, it would send out ripples. But after about 500 and 380,000 years after the Big Bang, suddenly the universe became transparent, and the pressure for these sound waves suddenly vanished. So the ripples caused by different sound waves suddenly stop having an effect, and you get this freezing effect. However, these ripples are still apparent. So this is the Baryona-Kuston oscillation constant. And basically what that means, and the constant is about 490 million light years. So basically, if you have things that have equal spacing, you can kind of see a pattern in it. And one way of seeing that, basically put points on a sphere, like these two, and then rearrange them randomly. So basically, we're taking one point and then another random point, and then we're summing up all those different length one vectors together randomly. And you always get something that looks like a galaxy distribution, which I thought was fascinating. So yeah, just take random points on a sphere, use those as vectors, order the vectors randomly, and then sum the vectors together to see where the placements are, and you get what looks like a galaxy pattern. The way they measure that is they basically have plotted where all the galaxies are, and they notice this big spike at one particular range for galaxy densities. So how might we communicate stellar mass? So the mass of our sun isn't particularly noteworthy. It's in the uh, realm of a whole bunch of different stars that are slightly more and slightly less. It's a Hertzsprung-Russell diagram has a whole bunch of different stars, but for constants, one thing you can look at is stellar remnants, white dwarfs, neutron stars, and black holes. It turns out that the peak for white dwarfs, which I show here, is right at about 0.55. So this is the peak of the mass distribution of helium white dwarfs. And let's call that W. W is the peak mass for white dwarfs. If you go to 2W, that's the lightest neutron star, and it's also the heaviest observed white dwarf. There's a tiny overlap between the lightest neutron stars and the heaviest white dwarfs. The heaviest possible white dwarfs is 1.4 stellar mass, but they almost never get that far. The peak is here at 5.5. They very rarely get above 1 or 1.1. There's a few known that are 1.1 or 2W. If you go to 3W, 3 times the peak mass of a white dwarf, 3 times gives the peak mass for neutron stars. and 4W is the maximal for neutron stars. I thought this was a very nice, simple item. So I'm going to call this the stellar mass constant, the peak mass of helium white dwarfs. Because if you get 1W, 2W, 3W, 4W, you get items that are easily observable anywhere in the universe. The usual mass of a white dwarf, the heaviest for neutron stars, and lightest for neutron stars, heaviest for white dwarfs, the peak for neutron stars, and the maximal for neutron stars, and the minimal for black holes at 2.2 stellar masses, or 4 times W. What else can we use for mass? There's the various element constants, protons, neutrons, electrons, things like carbon. We could go to quarks. We can also make dangerous spheres. These are different elements you can use to make very dangerous spheres at the critical mass. There's also the potato limit I mentioned, which is about 10 to the 19 to 10 to the 20 kilometers. The largest known irregular one is Proteus, an inner moon of Neptune. Here's a picture of it here. It's 400 kilometers, and it weighs about 3 times 10 to the 19th kilograms. The smallest known spherical we know about is Mimas, a moon of Saturn, which is 3.75 times 10 to the 19 kilograms. So it's right in there where the potato limit is for mass. So I'm going to call that the not a potato mass, and we're estimating it at 3.6 times 10 to the 19 kilograms, and that is E times N to the MP divided by A. So that's one way of getting to something that is close to the potato mass, but I just made this up. But it's still based on physical constants. We can get various masses. Here's where the brown dwarf starts. These are various places in stellar masses for non-remnants, things that are still burning. Red dwarfs, red giants, and where a supernova starts. Only bright and fiery globes know more luminosity than you. I didn't like the old mnemonic, so I came up with a new one. So this is a chart of the different stellar classifications, O, B, A, all the way to Y. And these are some sample stars of those types. At the other end, we've got biological sizes. So if we look at our cells, our red blood cells are somewhat interesting as mammals. They don't have a nucleus in them. Other animals, like fish, their cells do have a nucleus. Mammals have an advantage because our blood can be smaller, which lets us survive things like dehydration better than other animals. So the usual size for a nucleated cell, a cell that has a DNA nucleus, is 10 micrometers, about the thickness of plastic wrap. Gold leaf is 0.1 micrometers, and 10 micrometers, the size of the smallest cells with a nucleus, is 1/100th of a millimeter. So plastic wrap, aluminum foil, all have about the thickness of one of our smaller cells. But pretty much all our cells are in the range of 10 micrometers to 50 micrometers. And it's expected that for other forms of life, cells would basically have the same size. We're not sure of this, but that's the guess. In addition to sizes, there's also time for cells. And the time that seems to be the clock on for cells is the millisecond. And that's the speed for an ion channel gating. If you have one of your cells has a ion coming into it, the time it takes to get through the membrane of your cell is 1 millisecond. And pretty much everything else is a multiple of that. Uh, a, uh, a single step for a kinesin motor protein. Basically, you've got these kinesin proteins moving things around in your cell, and it basically is walking on various strands of DNA. The time it takes to take one step is 6 milliseconds. And I've got timings for all these various items that take place in the cell. Some of them take a second or longer. So it takes about 1 second for oxygen to load and unload from a red blood cell in your capillaries. We can also look at temperature and pressure as something that has replicatable standards anywhere in the universe. The triple point of a substance and its critical point. So these are different triple points. For example, for water, it's at a pressure of 0.6 kilopascals at 0.01 degrees Celsius. That's the triple point for water, where the vapor, liquid, and solid can all occur at the same time. There's also a critical point where it is between gaseous and compressible, but it's about to go supercritical. And these are different critical points for items. For water, it's at 373 Celsius and a pressure of 217 kilopascals. Another item that has constants is the superconductance temperature. So for lead at a temperature of 7.2 Kelvin, it becomes superconducting. Electrical resistance vanishes and magnetic fields are dispelled. And we can go up to the current best known superconductor at easily replicatable pressures is mercury, barium, calcium, copper oxide, which has a supercritical temperature of, or a superconductance temperature of 133. But that's not the leader, though. The leader is lanthanum decahydride, which has a transition temperature of about -10 Fahrenheit or 250 Kelvin, but it's only stable at a pressure of 150 gigapascals. So it's not something you want to use all over the place, since it's very difficult to get a pressure that high. One item that I like playing with in I've got a novel, and I wanted a good stable currency. And I decided to use the Planck energy unit, which is about equal to a tank of gas or a lightning bolt or a half a ton of dynamite. This 1.9 10 to the 9 joules. I use the Pluto symbol because it's PL again. But instead of Percival Lowell, this is for Max Planck. The buying power of this tank of gas, for example, in 1925, it was about $3.36, and that was pretty much the same price as 2 weeks of food. And here I've got various prices of food from 1925. Diverged a bit in 1950, but now it's basically the same. The buying power equivalence of a tank of gas and 2 weeks of food, if you are willing to be not the best food, but these are all okay for food. For the past 100 years, the Planck as a item for equivalent between eating and a tank of gas has been very consistent, much more than any other currency. So I think something based uh, on a Planck as a currency might be interesting. So that's what I used in my novel, the Planck energy unit, which was developed by Max Planck. It's based on the Planck constant to the fifth times the fifth power of the speed of light divided by g. The square root of that is the Planck energy constant, and it's equal to about a tank of gas. One bit of sad news, one person that helped me with this column is Michael Trott, who sadly died last week. I showed his column for the Planck constant earlier. Here's a picture of me here next to Michael Trott with Cheryl Houghton of the TV show Numbers, Eric Weinstein, and Amy Young. And we were there at the State Department to pick up the Carl Sagan Award for the Public Appreciation of Science for our work on numbers. And here's various other pictures of Michael Trott. And these are all links to the columns that he wrote. Here he is with a picture next to the SI unit conference in 2019. He was actually at the constant. And this talk is already online. If you want to take a look at it, there will be a link from this YouTube link to the talk, but you can also just go to community and it'll be at the top. So that's what I had prepared, and I'll be glad to answer any questions if anybody has any. Yeah, the text version of this is at community right now. So if anyone has any questions, I guess we can wrap things up there. Many thanks, everyone.